Okay, so in last class, so far what we have done, so the problem that we are really looking at is this problem Ax is equal to B, where we decided A is a matrix of the size m cross n and B is a given vector of size m. Then the problem is that first, does there exist an x such that Ax is equal to B? And if such an x exists, then is that x unique? Okay, so existence and uniqueness of solution to the system of linear equation, that is something that we understood. Then what we did, then we took our first step towards actually computing the solution of this system of equations Ax is equal to B. And what did we try to understand? We tried to understand several things. So for past couple of lectures, we have been discussing about left invertibility, right invertibility, invertibility of matrix A, right? So these are the concepts that we have introduced, and we see that these concepts actually generalize the concept of inverse of a real number, correct? So inverse of a real number is actually generalized by these concepts in the case of matrices. That's what we see. That's what we saw. And a not equal to 0, a not equal to 0. What was the equivalent criteria for a not equal to 0? So left invertibility, you saw the matrix is left invertible if and only if the columns of A are linearly independent. Or right invertibility, like you take transpose, so a not equal to 0, the equivalent condition for right invertibility was the rows are linearly independent. And for invertibility of the matrix, it was like both rows and columns are linearly independent, right? So invertibility was for the square matrices. Left invertibility you saw at best wide, at best tall or at best square. And right invertibility was basically for wide matrices at best square, right? So that's what we actually saw so far. Then we saw that left and right inverses are not unique, but we saw that if left and right inverse both exist for a matrix A, then clearly from the dimensions that we have understood, the matrix A should be a square matrix. And moreover, this left inverse and right inverse, they are actually unique. They are same and they are unique, and that we call inverse of a matrix A, right? So we understood what is inverse of a matrix A. And once we had these inverses, we saw how can they be used in computing the solution Ax is equal to B. So we had several ways, different ways in which we could do that. And we also got introduced to one interesting matrix which is called as Gram matrix towards the end of last class. So suppose A has linearly independent columns. A has linearly independent columns. Then we computed this A transpose A matrix, and we show that A transpose A is invertible, right? So these two statements actually were equivalent, right? So this, then I can say actually these two statements were equivalent, right? We actually proved these statements in last class, that A has linearly independent columns if and only if A transpose A is invertible, right? So that was something that was very interesting. And now we have also shown that if A has linearly independent columns, then A is left invertible. How do we actually do that? We use this particular result, right? So what is the result? So we construct a matrix B, which is A transpose A inverse A transpose. Because the given matrix A has linearly independent columns, A transpose A is invertible. So I can actually compute the inverse of that matrix. This is that matrix A transpose A inverse, and I multiply it to multiplied by A transpose, right? So if A is a matrix which is of the size m by n, A has linearly independent columns. What does that mean? That means that the matrix looks like this. Either it is a tall matrix or it's a square matrix at best, right? So m cross n linearly independent columns. This is the way A looks like. So A transpose is this matrix multiplies to A. So this is A transpose. So you get a square matrix which looks like this. So this is A transpose A. The inverse of A transpose A will also have the same size, and this A transpose A will get multiplied right on A transpose, right? So what is the size of A transpose? The size of A transpose is a wide matrix, right? So this is how this matrix will look like. So the product will look like this. So the matrix B, it has shape which is this. This is nothing but n by m shape, right? So this is n by m because this is n by n, this is m by n, this is n by m. So I have drawn the picture, but if you really want to write the sizes, these are the sizes, right? M by this is n by n and this is n by m to give you n by m matrix, right? So this is how the B will look like. So A transpose A inverse A transpose is this particular matrix, and the claim is that this particular matrix B, which is A transpose A inverse A transpose, is actually a left inverse of A, and it's not very difficult to check. So what is BA? That's all you have to calculate, right? So BA is identity. You can very easily see BA is equal to identity. So B is a left inverse, and this particular left inverse is a very special left inverse. It is called as pseudo inverse of A. Okay, so this is called as pseudo inverse of matrix A. Okay, so we'll see this pseudo inverse is going to play a very crucial role in entire least squares problems that we are going to study in this particular course. Okay, so this pseudo inverse is very important for us. So this is what we have covered so far. So is there any doubt about what we have done so far? If whatever calculations we have done so far, any results that are not clear? Because these are the things that I'm going to now repeatedly use, and I'm going to build arguments based on these results that we have. Okay, so especially understanding least squares problem depends on the results that we have solved so far. So I just want to make sure that you understand these things. So this discussion is clear so far. Okay, in that case, we move forward, and we actually see how the computations are actually done. Okay, so computations are done in a slightly different way. Okay, computations. So suppose I have to solve Ax is equal to B. Okay, system of linear equations. For the time being, I consider A is a matrix which is a matrix of size m by n. Okay, square matrix. So I have square matrix A, and B obviously is a vector in Rm. Okay, and then I am trying to solve Ax is equal to B. So how do I really compute? So first I check whether the columns are linearly independent or not. So checking whether the columns are really linearly independent or not, it's a difficult task, right? So theoretically, it's good to say that columns are linearly independent or not, but how do you really check them? How do you really compute and see whether the columns are linearly independent or not? Okay, so for that, and computing inverse also is not really that straightforward, right? So in order that so like one way to compute inverse was like yesterday's class, I think we saw this. So there are, I think we discussed this in yesterday's class. Yeah. So every time in order to compute the inverse, so these BIs are actually the columns, right? BIs are the columns in the inverse of A. So in order to compute each column, you have to solve this system of equation, right? So so this is like a very difficult problem now, right? So if you want to compute the inverse, then this is what you do. But this is same as solving a system of linear equations problem, right? You have to find out BI such that ABI is equal to EI. So now this is like catch 22 problem. In order to solve a system of linear equations Ax is equal to B, you are saying you want to compute A inverse, which is B. And how do you compute B? In order to compute B, again, you are solving another system of linear equations with coefficient matrix, right? So now this is like really weird situation, difficult situation. So how is typically these computations done? Okay, so I will take a particular case. So what is the particular case that I will take? So I will look at a particular system of linear equations. So suppose I have this matrix X is equal to B. Okay, so this vector is X. Okay. And I have these matrix entries U11, U12 up to U1n. Then U21 up U22 up to U2M, and so on and so forth up to UMM. And all the entries below diagonal are 0. Okay, all the entries below diagonal are 0. What is this matrix called as? This matrix is called as upper triangular matrix. If all the UII not equal to 0, for I is equal to 1 to up to M, can you say that the matrix will have full column rank, or the column space will be entire Rm? Can you say that? Do you see this, how it is going to be?
Yes.
So if all the diagonal entries are non-negative, all the diagonal entries are non-zero, then the matrix has full rank. The matrix has its columns which are linearly independent, and if the columns of the matrix are linearly independent in that case, then what can you say? You can say that for any given B there exists a unique solution X such that this matrix I will call U, this matrix I'll call Ux is equal to B. What is the advantage of this particular triangular system? The advantage of this particular triangular system is that from here you can solve the system of linear equations very easily. Why? Again, let us write down U11, U12 up to U1m, 0, U22 up to U2m, then so on and so forth, 0, 0 up to UMM into x1, x2 up to xm is equal to b1 up to bm, correct? This is the system of linear equations that I am having. And what do? I now look at the matrix vector multiplication as inner product, right? So what is the first entry? The first entry of this matrix vector multiplication is this inner product. And with the same logic, what is the last entry? The mth entry. The mth entry is this multiplied by this, correct? So I'll write the last mth entry first. And what is that? UMMXN is equal to all these guys, and last I have BM. So from here, I will be very easily able to calculate what is XM. I will very easily calculate what is XM. XM will be equal to 1 upon UMM into BM. Is that correct? I have already assumed that the diagonal guys are not equal to 0 to ensure that the columns are linearly independent. So there is no problem in dividing by UMM. I will divide by UMM, no problem. So I get XM. Then what is the second last equation that is going to be there? The second last equation in this sequences. So m minus 1th equation. After m, I will look at m minus 1th equation. So UM minus 1, m minus 1. Xm minus 1 plus UM minus 1m Xm is equal to Bm minus 1. Is that correct? That's the equation that I'm having. And now I already know what is the value of Xm. What is the value of Xm? I already calculated it from here. This is the value of Xm. So I can solve this equation for Xm minus 1. And how do I do that? I will solve Xm minus 1 is equal to 1 upon Um minus 1, M minus 1. Again, check that this entry 1 upon Um minus 1, M minus 1 is a diagonal element. I have already assumed that diagonal entries are not equal to 0. So if that is guaranteed, then Xm minus 1 is actually equal to this. Bm minus 1 minus Um minus 1 M Xm, and Xm I already calculated from the previous case. And now you see what is going to happen. I'll look at m minus 2th equation. M minus 2th equation will involve only m minus 2, xm minus 1 and xm, out of which xm minus 1 and xm are already known to you, and you will only look at xm minus 2. So you'll get a similar equation like this, and you can continue all the way up to the first equation. And then you will be successively finding out the values of xm, then xm minus 1, then xm minus 2, so on and so forth, all the way up to x1. So this particular way of computing the solution is actually called as back substitution. What is this called as? Backward substitution. Okay, so this is called as backward substitution. So what we are really doing, is that we are taking advantage of a very special structure. Okay, the advantage of very special structure, upper triangular structure of this matrix U, and we are making sure that the columns of U still span the entire space Rm by saying that all the diagonal entries Ui are not equal to 0, and then here it is really very easy. So now that you know there is a unique solution, so solution, one way to express was x is equal to u inverse b, or if you compute x using this backward substitution method, you are basically computing inverse of the matrix U, but you are computing it in disguise. You are not explicitly computing the U inverse. You are computing it in disguise, and still you are getting the values xn, x1, x2, x3 up to xn only in the backward sense, right? You first calculate xn, then xn minus 1, so on and so forth. So this particular structure U happens to be a very interesting structure, upper triangular matrix. Why it is called upper triangular? Because everybody above the diagonal, okay, everybody above the diagonal. So if you see the way entries are, the entries are here in this triangle, right? And this entries are all 0, right? These entries are all 0. So it's like a triangle, upper triangle above the diagonal, right? So this is an upper triangular structure. Similarly, you will have a lower triangular structure as well. So the lower triangular structure will also be equally easy if you want to compute the solution of system of linear equations. So it looks like if you can find out certain structures which are spatial, so those structures if we call canonical structures. So if such canonical structures or spatial structures are available with us, okay, then solving a system of linear equations is really a very easy task. Here, the solution can be obtained very easily, very quickly, using something which is called as backward substitution method. Okay, using backward substitution method, you can very easily compute the solution here. But unfortunately, what is the problem? Unfortunately, the problem is that almost always when you want to solve the system of equations Ax is equal to b, the given matrix A will not be in this canonical form. It will not be an upper triangular matrix, or it will not be a lower triangular matrix. Then what should we do?
So we can break it into.
Yes, Vinay, go on.
We can convert it into
Convert into what?
upper triangular matrix.
But when you convert a given matrix into upper triangular matrix, what might happen?
Equations get exchanged.
Equations will get exchanged, but what is the guarantee that you should have? The solution should not change, right? The solution that you are seeking should not change. But you somehow try to bring the equations into spatial canonical forms without changing the solution. So what we really want to do is that given Ax is equal to b, okay, so unfortunately we will not have A in the canonical form, but having the system in canonical form looks like a very interesting thing. So what we are going to do, we are going to ask this question: given Ax is equal to b, what can we do? Can we transform this system of linear equations in canonical form? So what is canonical form? Where accompanying matrix is upper triangular or lower triangular. So upper triangular system, we'll just call this upper triangular system or lower triangular system. Okay. So what will happen if we are really able to do this? What will happen if we are really able to do this is that this system of equations will get transformed to that canonical form. So what is the condition? Provided the solution of the transformed system does not change. Correct? So we don't want to change the solution. Okay, you want to convert A into a canonical form, but you don't want to change the solution X finally. Okay, so that is something that we'll do. So if we are able to transform this system of equations Ax is equal to B in a very nice canonical form, then that canonical form can be solved very quickly, very easily, and we will be able to get the solution. Okay, so this is the idea. So this is what we are really going to do. So have you ever encountered any such canonical form transformations or any methods previously that give you these canonical forms? Have you seen anything like this before?
Gaussian elimination.
Huh?
Gaussian elimination.
Gaussian elimination. So what happens in Gaussian elimination? What happens in Gaussian elimination? You are right.
We try to convert it into a row echelon form.
You try to convert the given system of equations into row echelon form. So row echelon form, basically you will get upper triangular form. Okay, so if the system, if the matrix is like invertible or the columns are linearly independent, that's what we are assuming for the time being, then you'll get a triangular form. So it's a canonical form. Correct. Any other method you have encountered? Have you seen any other method? Only Gaussian elimination you have seen? No other method you have seen before?
LUX decomposition.
LU decomposition. Okay, so what is LU decomposition? What is LU decomposition? You are right, but I just want to know what is LU. Vinay?
We compute a left matrix. That we will calculate the inverse of the LUX, assuming LUX.
Okay. What else? Any other method you know? You know only these two methods? You don't know any more methods? So what Gaussian elimination, Kshitij already told. What Vinay is trying to say is that in LU decomposition, what we are trying to do is try to write down A as product of LU, where L is a lower triangular matrix like this, and U is an upper triangular matrix like this. Okay, LU. That is what he's saying you try to write down. Then AX is actually LUX. So he's saying you take UX is equal to Y, for example, and then LY is equal to B. That is what you have, right? AX is equal to B basically means LY is equal to B. Then you solve LY is equal to B, but what is the advantage in solving LY is equal to B? When you solve Ly is equal to B, it's a lower triangular system. You see, this is the L. So you have a lower triangular system, so you can do forward substitution, a process opposite to what we just saw here, and then you can find out what is Y. Once you know what is Y, you come back to that Y here, substitute that value of Y here, and solve this system Ux is equal to Y. And what is the advantage? The advantage is that now this Ux is equal to Y, U is basically an upper triangular system. So by doing backward substitution, you can calculate calculate X, which is the actual solution, original solution that you wanted to find out. So what is the objective? The objective is to write down matrix A in this particular form L times U, lower triangular times upper triangular. Is that what you mean, Vinay, when you say LU decomposition?
Yes, sir.
So basically the challenge is to come up with such a decomposition. It's highly unlikely, right? Non-trivial to write down this LU decomposition. Given a matrix A, being able to write down it as a product of a lower triangular and an upper triangular matrix, it looks like a challenging task. At the same time, you have to make sure that all the diagonal entries in this L and U, they both are actually non-zero, right? Because Otherwise, if they are 0, then your procedure will break because you are going to divide by the diagonal entries here. So if you are going to divide by the diagonal entries, you have to make sure that the diagonal entries are not equal to 0. So that also guarantees requirement. But by some hook or crook or by some way, you are able to compute this LU decomposition. For example, if you are able to compute this LU decomposition, then your job is done, right? So that is what you are saying. Excellent. So this is one method. So you know already two methods: Gaussian elimination and LU decomposition. What is one more method that you know already?
Sir, QR method.
What is QR method?
Hello. Sir, Q is orthogonal matrix and R is upper triangular matrix, and we can write the matrix in that in the term of product of orthogonal and upper triangular matrix.
So you mean QR decomposition?
Yes, sir. Yes, sir.
Okay, so QR decomposition. So in QR decomposition, what you are proposing? You are proposing you write down matrix A as product of two matrices, Q into R, where Q is an orthogonal matrix and R is a upper triangular matrix. Is that what you are saying, Abhishek?
Yes, sir. Yes, sir. Yes, sir.
Okay, so if you do this, then AX is equal to B. What does this really mean? Instead of A, you can write down QRX is equal to B. Because Q is an orthogonal matrix, what you are going to do, multiply by inverse of Q on both sides. But now you will say again, I have to compute inverse. But computing inverse in case of orthogonal matrices, we'll say is very easy because the inverse of orthogonal matrix is its transpose. So we will have Rx is equal to Q transpose B. That's what you are saying. So R is an upper triangular matrix. Now it's easy, right? Again, do the back substitution and then you will find out what is the solution. Rx is equal to Q transpose. So this is what you can do. So these are three methods. Okay, these are three methods. Very nice. So these three methods, I'm happy you know these three methods. These are the three methods that we are quickly going to summarize, quickly going to understand. So I will claim that you have already seen all these three methods in your Maths 2 course. Okay, all of those who have taken second semester mathematics course, you have seen these methods. Can you tell me, is this right or wrong?
Yes, sir.
So Gaussian elimination and LU decomposition you saw. Did you really learn QR decomposition in Maths 1, Maths 2?
No, sir.
Yes.
Huh? Yes or no?
Sir, I have studied it. I have studied it in my master's and
Yeah, so
in my BSc in third year.
yeah, you have studied at some point of time. That is fine. But like BTech students, have you studied it in Maths 2?
No, sir.
I am saying you have. Have you studied Gram-Schmidt orthogonalization process in Maths 2? That you have studied definitely, no? Gram-Schmidt orthogonalization?
We had studied this in linear algebra.
Correct. It was in linear algebra course. So this Gram-Schmidt orthogonalization that you have studied, that is exactly same as this QR decomposition in case of matrices. Okay. So Gram-Schmidt orthogonalization that you have studied and QR decomposition are no two different things. The only thing is that Gram-Schmidt orthogonalization computationally can be a little challenging. QR decomposition is computationally very good. It's stable. Okay, so that's why QR decomposition is something that you do with matrices, which is basically same as Gram-Schmidt orthogonalization. What happens in Gram-Schmidt orthogonalization? In Gram-Schmidt orthogonalization, you are given a basis of the vector space and you try to construct an orthogonal basis from the basis that you already have, right? And the orthogonal basis, how do you construct? The way you construct, you pick the first element of the basis, the span of that and span of first orthogonal basis element should be same. Then you take the first two elements from the basis, their span should be same as span of first two elements in the orthogonal basis, and so on and so forth. That's how you construct. If you see the columns of A, if they form the basis of Rm, columns of A, if they form the basis of Rm, then the columns of Q also form basis of Rm and they are exactly constructed the way you want them to be constructed in Gram-Schmidt orthogonalization. So this QR decomposition actually is Gram-Schmidt orthogonalization. Okay, so there are so many beautiful connections between these concepts that you have studied. So we will look at these three important look at these three important things. Okay, and possibly at the end of today's lecture, you will see that these two are also not really two different things. Okay, so have you encountered this before? Have you seen that Gaussian elimination actually is same as LU decomposition? Do you know that? Have you already seen that? No? Okay, let us see that. Okay, so let us do this thing. So now you understand what we are going to do. So what we are going to do, we already understand AX is equal to B, system of linear equations, existence uniqueness we understand. We understand how to express solution X in terms of different inverses of matrix A also, left inverse, right inverse, or inverse, and so on and so forth. But turns out that using those inverses to compute the solution, the challenge is to compute inverse, which is a difficult problem. And the way we understood those inverses, turns out that in order to compute those inverses, you have to solve a system of equations again. So it's like a catch-22 problem. We don't want to get into that. So we want to come up with a different technique to solve AX is equal to B. So we saw one particular structure of a canonical structure, which is upper triangular or lower triangular. And if you have matrix A in that canonical structure, then it turns out that solving the system of linear equations is really very easy. So what is the objective now that we have in our mind? Unfortunately, any arbitrary system of linear equation, when you encounter X is equal to B, it is not in the canonical form. But the idea now is that can you do some transformations? Can you do some transformations so that you transform this system of AX is equal to B to an equivalent canonical system which can be solved very easily? Okay, what is the key statement? You have to transform AX is equal to B into an equivalent canonical system. Equivalent meaning a equivalent system of linear equations whose solution will be same as AX is equal to B. So here you saw, right? You solved two system of equations. Here also you solve this. Instead of AX is equal to B, you will solve RX is equal to Q transpose B. So this RX is equal to Q transpose B basically is the equivalent transformed system, right? And why it is easy? Because you just have to do the backward substitution with respect to the upper triangular matrix R, and once you do that, you find the solution. Okay, so that's the whole idea. So now if you are able to transform these things very nicely, efficiently, in a computationally stable way, then we would be solving system of equations AX is equal to B very easily. So the first thing that we are doing here is we are focusing only on the square systems. But then later on, when we go to QR decompositions, I will also show that you don't have to restrict yourself to a square system of linear equations. You can have a rectangular system of linear equations also, and you can apply these things and find out the solution. Okay, so this is what we are really going to look at. So in next couple of lectures, these are the decompositions that we are going to study, and I hope you appreciate why we are going to study these decompositions. So that's fine. Any comment here? Any observation? Anything that you want to relate to that you have seen earlier with these things?
Sir,
Yes.
sir, is square method is same as LU decomposition? I mean, A
What
can be
method?
right square root method. I mean, A can be right as L transpose where L is a
So
lower
that
triangle.
happens. You cannot write every A as L transpose. Only square and symmetric matrices A can be written as LL transpose. Okay, and there also you can solve LL transpose, that system of linear equations you can solve only when A is something that they call positive definite. Okay, so if A is positive definite, then you can write uniquely A as LL transpose, so that U becomes L transpose. U is an upper triangular matrix. That upper triangular matrix, which happens to be transpose of the lower triangular matrix L that you have here, and that particular decomposition is called as Cholesky decomposition. Okay, so the square root method that you are saying, it is called as Cholesky decomposition, but that is only for a particular class of matrices which are positive definite matrices. Okay, so they are symmetric and they have additional property of being positive. But you are right, so that you can think is a particular case of LU decomposition, the Cholesky decomposition.
Thank you.
So because you mentioned it, I'll just say, so these decompositions, na, so Cholesky decomposition, LU decomposition, QR decomposition, eigenvalue, eigenvector decomposition, and singular value decomposition. Okay, these are the 5 important decompositions that you will encounter in any matrix algebra. Okay, like matrix algebra, these 5 decompositions are like very fundamental in matrix algebra or linear algebra if you want to call. And these are the 5 important decompositions that will always come up in any data science or like AI, ML, DL type of applications. Okay, so these are the type of decompositions that are really very important. We are going to look at all these decompositions in this particular course, and on top of it, we are going to study something which is called as low rank approximations or low rank factorization, low rank decompositions. They are also something that are really important. So we can relate them to SVD. So that's why I'm not mentioning them differently. But these are the other type of decompositions or approximations or the problems that we are going to see, which are related to singular value decomposition. So this principal component analysis you can relate with eigenvalue, eigenvector, or singular value decomposition. And least squares problem you can relate to this QR decomposition. That's what we are going to do. Okay. So these are the 5 fundamental decompositions in a matrix algebra course. And Cholesky decomposition in a way is a particular case of LU. So I'm not going to separately deal with it. So I'm going to look at LU and QR. So in next couple of classes, we are going to cover these 2 of the 5 important decompositions. Okay, so that's the plan. That's what we are going to do. Any other comment? Anything you want to say? Okay. In that case, we move forward and we actually go on to see how we are going to do this LU decomposition. Okay. So what I am really going to do is the following. LU decomposition. What I'm going to do is really the following. Suppose I am given a matrix A, which is a square matrix. Okay, suppose I am given a matrix A, which is a square matrix. What I am really going to do is I am going to construct these M matrices. Okay, rather M minus 1, not M. I am going to construct these L1, L2, Lm minus 1. These are the matrices that I am going to construct somehow in such a way that I get an upper triangular matrix on the right hand side. You understand what I'm going to do? So I'm going to construct, okay, I'm going to construct Lm minus 1, Lm minus 2, L2, L1. Okay, I'm going to construct these matrices such that, okay, such that this statement Lm minus 1 up to L2, L1 product times A becomes U, where U is upper triangular. Okay, U is upper triangular. And what is the property of this L1, L2 up to Lm minus 1? I am hoping that I will be able to call all of this to be L inverse such that this L is lower triangular. Okay. Okay. To prove, I want to prove that the construction I am going to make, of this L1, L2 up to Lm minus 1 is going to be such that I call this entire product Lm minus 1, L2, L1 as L inverse, and then I take inverse of that L, then L is lower triangular. So if that is true, then I would have to prove, if that really happens, then I will have L inverse U is equal to A, which implies A is equal to LU. And then L is the lower triangular matrix. That's what I will prove. And U is an upper triangular matrix. That's going to be given by the construction. The construction itself will guarantee that U is equal to upper triangular matrix. That is what I am really interested in doing. Is that clear what I'm going to do? So I will start with the construction. Okay, so I will start with the construction. So so what will be like a simple thing that you can observe is that this L will basically be equal to L1 inverse, L2 inverse, so on so forth, Lm minus 1 inverse. Okay, so that is what this thing is. Now you will say that okay, you wanted to avoid computation of inverse. You wanted to avoid computation of inverse, that's why you are doing LU, and here everywhere you are writing inverse. This L inverse is there. Then you are, in order to compute this L, you are going to do multiplication of several inverses. Is this an advantageous thing to do? So we will see in this particular case, the construction that we will have is such that you automatically becomes upper triangular. Computation of all these inverses is no big deal. You can do it very nice. Okay. So what is really going to happen? So what is really going to happen? You can see pictorially. Suppose I am looking at a 4x4 matrix. Okay. So this is, I am just representing these entries like this. So I am looking at 4x4 matrix like this. Okay. So this is the given matrix A that I have. So to this matrix A, I multiply by a matrix L1. Okay. To this matrix A, I multiply by a matrix L1. And after multiplying by this matrix L1, okay, what I am expecting to get is this. I'll get a 0 here. I'll get a 0 here. And I'll get a 0 here. Okay. By multiplying by L1 on the left. So this matrix basically is L1A. And these stars actually, what you can think of is that these are of different color. Okay. So every time I'll not make them of different color, but for the first time I am doing. So what is really happening is that these are the entries that are changed from the original matrix. Okay. All other entries are actually same, and you introduce 0, 0. And then I am going to construct L2. I am going to construct L2 in such a way that this thing happens. What happens? This first row and first column does not change. But now I look at this 3x3 blue submatrix, and what happens to this 3x3 blue submatrix? It gets changed to this form. So this is L2, L1A. And you catch the drift of what is really happening here. Then I will do one more thing. I will apply L3 on this. So I will multiply by some constructed matrix in such a way that what I am going to get here is this, right? So I will not change this first 2 rows and first 2 columns now. So this remains unchanged, and only this. So here, when you wanted to apply L2, you focused on this block. When you want to apply on L3, you will focus on this block. And what will you change in this block? This block will change in such a way that you will get this, which is nothing but L3, L2, L1A. So this is the matrix A, and the construction itself shows that this matrix is an upper triangular matrix, right? So the matrix that you will obtain anyway after this construction is going to be an upper triangular matrix. So the only challenge now we have is to actually compute what is L1, L2, L3. Once you compute what is L1, L2 and L3, then what is going to happen? The matrix U that you get is going to be an upper triangular matrix. By construction itself, you can see that. So there is nothing left to prove with respect to U. Now what is left to prove with this is that this matrix that you get, which is L inverse, is such that when you multiply it by A, so when you write down A is equal to LU, which is nothing but L1 inverse, L2 inverse, L3 inverse into U, this product is actually a lower triangular matrix. If you are able to prove that, then you get the LU decomposition that you desired. And once you get the LU decomposition that you desired, then your job is done. So is that okay? What I'm going to do through the pictures, do you understand? So many a times in this course, I will try to use these pictures to indicate what operations on the matrices we are really going to do. Okay. So I hope this much is clear to all of you. So this is what we are going to do, and we are hoping that this L1 inverse, L2 inverse, L3 inverse are not really difficult to compute. At the same time, we are hoping that this L1, L2, L3 are like interesting matrices which will give rise to this lower triangular matrix and so on and so forth. So that is what we are going to do. Okay. So Now that the idea is clear of what I am really going to do, let us take a 4x4 matrix example itself. Okay, so before writing down the algorithm or telling the procedure, let us work with a matrix which is 4x4 matrix. Okay, so I have this matrix 2 1 1 0, then 4 3 3 1. So I have this example with me, 4 3 3 1, 8 7 9 5 and 6 7 9 8. Okay, 6 7 9 8. So this is the matrix A. This is the matrix A, which is 4x4 matrix. Okay, this is the matrix A, which is 4x4. So now I say the first step here now is I want to find out the matrix L1. Okay, the matrix L1 should be such. The matrix L1 should be such that when I multiply L1 to this matrix A, I get this particular form. L1A form is that I get zeros before the 1/1th entry. That's what I really want. Okay, so that's what we want to do. So what are your thoughts? Can you tell me what might be the choice of L1? So L1A. So I have L1 here. So where have you seen this before, that you want to make all the column entries 0 below the diagonal entry? Everywhere that is what is happening, right? In the first place, all the entries below the diagonal element are being made 0. In the second case also, all the entries below the diagonal element of second column are made 0. And in the third case, all the entries below the diagonal element of the third column is made 0. Where have you seen this before?
The steps of Gaussian elimination we do.
The steps of Gaussian elimination. So this is something that we already have seen in Gaussian elimination. And now I'm using probably the same ideas that I know in Gaussian elimination to construct LU decomposition. So this is the step. So that's why I'm going to do it in this way, so that you can relate both the concepts that you have studied together, Gaussian elimination and LU decomposition. And you can actually see that Gaussian elimination actually is exactly same as LU decomposition. Okay, so if this idea is clear, then yeah, correct, while converting to row echelon. So now if this thing is clear in your mind, then what is the choice of matrix L1 that I'm taking? Okay, you see carefully. So I am writing this matrix L1 first. So what is this matrix L1? It is 1 1 1 1 identity matrix. Okay, this is an identity matrix, and in the identity matrix I am having -2 here, -4 here, and -3 here. All other entries are 0. In the identity matrix, obviously, this is the only change that I'm making. This is my L1. Okay, so this is my L1, and I multiply it to 8. So what is A here? A is 2 4 8 6 1 3 7 7 1 3 9 9 and 0 1 5 8. What will you get after this multiplication? Can you quickly do the multiplication and tell me what will you get? So you look at the matrix vector multiplication the way it happens. Okay, so if I want to compute what are the entries in the first column, what am I going to do? The entries in the first column, I will look at this row, first row of L1, multiply by the first column of A. When I do that, what am I going to get? I'm going to get 1. Is that right? Sorry, I'm going to get 2. The entry is not going to get changed. What happens to the second entry? The second entry, I'll look at the second row of L1 and multiply it with the first column of A. So when I multiply this, what do I get? -2 into 2, which is -4, plus 4, 0. And because of these two zeros, I'll get 0, 0. So I'll get a 0 here. Now go to the third entry below the diagonal, -4 0 1. You multiply this here. What are you going to get? -4 into 2 8, 0 into 4 0, 1 into 8 8, 0 into 5, 0 into 6 0. So what are you going to get? You are going to get another 0, and similarly here also you will get 0. Is that correct? So by having this particular matrix L1, what I have achieved really is that I have achieved this particular guy which is unchanged, and I have been able to introduce 3 zeros here. I have been able to introduce these 3 zeros. Just these 3 zeros are introduced here. And now you continue with this matrix vector multiplication, you will realize that I actually do not change the first row of this matrix because I am multiplying by E1 transpose anyway. You look at this particular vector, this is E1 transpose, right? First row of L1 is E1 transpose. That makes that I will not change first row of the matrix A when I multiply by L1. Are you following the calculation? And the other entries that I have here, the other entries, if you see, if you calculate, I get these entries. These are the same entries that you would have gotten if you were doing Gaussian elimination really. So you see now what has really happened is that there is no coincidence that I chose a -2 here, -4 here, and -3 here. Can you tell me how I chose these numbers sitting over here? How did I choose those numbers?
By making 1 in the first row, divide by 2 and minus 0.
So I wanted to introduce a 0 here. I wanted to introduce to 0 here. You know, in Gaussian elimination, how do you find out the multipliers, right? So those multipliers basically are those -2, -4, -3, correct? Once you know those multipliers, then your job is done. This is how I constructed L1. And what entries I wanted to make, 0? The entries that I wanted to make 0 were A21, A31, and A41. So I introduce L21, L31, and L41 in the identity matrix, right? The encircled entries, exactly at those places I introduced them. I made the entries that I wanted to make 0, and I get this matrix. Now, what is the next step? I have this L1A. So you see, I have this L1A. Now, what is the job that I have? The job that I have at my hand is that now I want to construct an L2 such that L2 into L1 is equal to L2 L1A has this particular form, right? So that is what I want to do. So now I don't want to change my first row and first column. Okay, so now you look carefully. What is the construction of L2 that I am doing? Okay, so this is the construction of L1. So now L2 L1A. Okay, so that is what I want for L2 L1A. So you carefully see what is the L2. So this is the identity matrix. I think there is a lot of echo. Somebody's mic. Ashwini Kumar, can you please mute yourself? Ashwani Kumar. Okay, never mind. I could mute yourself. Yeah, I could. Mute.
Yes, sir.
No, please mute yourself. So there is a lot of echo. Do you have any doubt? You want to ask something?
No, sir.
Yeah, please mute yourself. Okay. Thank you. So L2, L1 into A. Okay, that is what I'm looking at. And what is this? This is the identity matrix. And what is the change I'm making? I am precisely putting 2 entries in the identity matrix. At what position? At the position 3, 3. So this is 2, 2. So 2, 3 and 2, 4. 2, 3 and 2, 4 are the positions where I am making non-zero entries, and I have L1A with me. So L1A is 2, 1, 1, 0. Then I have 1, 1, 1, 3, 5, 5, and 4, 6, 8, right? So this is what I have. And if I multiply these 2 matrices, what would I get? What would I get is 2, 1, 1, 0. 1, 1, 1. This is also not changing, and now I'll get a 2, 2, 2, 4. Do you see? This is what is really happening. So what has happened? These 3 zeros were already there. You introduce these 2 extra zeros. What is the position of this 0? The position of 0 was 2, 3 and 2, 4. So in the identity matrix, these are the only 2 positions you changed. 2, 3 and 2, 4. These are the positions that you changed. And now again, what is this -3 and -4? How did you compute this -3 and -4? The -3 and -4 you computed by looking at these entries 3 and 4. And what was the row operation in Gaussian elimination that you were really doing? You were doing R3 minus 3R2 and R4 minus 4R2. That was the operation that you did. So the same operations, if you do on identity matrix, what is the matrix that you will get? This is the matrix that you will get. So do these operations on identity matrix, you will get this matrix L2. So you see, I am not bringing up these matrices by magic. There is this Gaussian elimination analogy going on. So these L1, L2, L3, all these matrices. Now you go back and think, how did you get this L1? How did you get this L1? So you see, what were you doing? You were doing R2 minus 2R1, correct? R2 minus 2R1. Then you did R3 minus 4, R3 minus 4R1, and you did R4 minus 3R1, correct? These are the three operations that you did if you are going to do Gaussian elimination. So you do these three operations on identity matrix. You do these operations on identity matrix. What is the matrix that you get? The matrix that you get is L1. So this is the matrix that you got as L1. Similarly, you can compute L2. Now L2, L1A is this matrix. Now you tell me what should be the matrix L3. Now you understand how I am constructing this. So you tell me what is the matrix L3. 1, 1, 1, 1. So what is the matrix L3 that you will get now? Are you following what I am doing? Huh?
Minus 1.
Minus 1 where? Minus 1 where? Where is the entry? So in L3, if this is my matrix L3, where should minus 1 come?
End of third column.
Last row, third column.
You give the correct coordinate, na? Where is the matrix entry? What is the place? You tell me what is the place.
4, 3.
4, 3. 4, 3 entry should be minus 1. And now what is your L2, L1A? 2, 1, 1, 0, 1, 1, 1, 2, 2, 2, 4. So this is the matrix that you have. 1, 2, 3, 1, 2. What will be the product that you will get? What will be the product that you will get? Is that what we will get? So clearly this by construction is an upper triangular matrix. Now there are several other things that we want to check. What are the things that we want to check? Now what we are going to do, so this is L2, L1A, right? So now what I have L3, L2, L1A is equal to U. So first thing you tell me, are these all L1, L2, L3 matrices invertible? Look at the L1 matrix. L1 was this matrix. Look at the L2. This is your L2. This is your L3. Are these matrices invertible?
Yes, sir.
Yes, sir.
Yes, sir.
They are invertible, right? Because the diagonal entries are all non-zero and the matrix is lower triangular. Diagonal entries are non-zero and the matrix is lower triangular. So the matrix is invertible in each of the cases L1, L2, L3. So the matrices are invertible. So I can write down A as, so how will I find out A? So I will multiply by L3 inverse first. Then I'll have L3 inverse here, like that I will multiply, right? So when I multiply like that, what will I get? I'll get L1 inverse, L2 inverse, L3 inverse into U. That is what I will get. So I will have A to be equal to this. So what are the things that I have to do? The first thing that I have to show is that L1, L2, L3 are invertible. So we observe that they are invertible. The next thing that we want to do is we want to compute L1 inverse, L2 inverse, L3 inverse. That is the second thing. And then what is it that we want to do? We want to take product of this L1 inverse, L2 inverse and L3 inverse together and show that this is lower triangular, right? Only then we will be able to say that we have achieved LU decomposition. U we have obtained, but we don't know about L. So what are the three steps now we want to do? So now to check what are the three things that we want to check. The first thing is that L1, L2, L3 are invertible. Second thing, compute inverses of L1, L2, L3. And third thing, show L1 inverse times L2 inverse times L3 inverse is a lower triangular matrix. So if you can show these three things, then our job is done. Okay, so the first thing, since L1, L2, L3 are lower triangular, they are lower triangular and diagonal entries are all ones, that is not equal to 0, L1, L2, L3 are invertible. Correct? So this first part you have shown, right? So now second part, you have to compute L1, L2, L3 inverses. Can you tell me what are the inverses of L1, L2, L3? This is my L1. Inverse of L1, if I say 1, 2, 4, 3, 1, 1, 1. Can you at least check that this is the inverse of L1? Can you at least check whether L1 inverse is this?
Yes, sir.
Huh? So what will be the inverse of L2? Can you guess? What is L2? Matrix L2 was minus 3, minus 4, right? Minus 3, minus 4 here. The inverse of this matrix, what will be the inverse? Can you at least check that this is the inverse? How are you checking it's the inverse?
Identity matrix multiplying.
You are multiplying this matrix with the inverse. You are multiplying L1 with L1 inverse and you are checking that you are getting identity. That's what you are doing. And similarly for L3 also. Similarly for L3 also, right? So not only that you have shown L1, L2, L3 are invertible, not only that you have shown L1, L2, L3 are invertible, you have actually computed the inverses of L1, L2, L3 also. And looks like computation of inverses of L1, L2, L3 is no big deal. Is it not? Whatever entries you are seeing here, you are just taking negative of that entry here. And when you take negative of that entry here, you get inverse. All other entries remain as is. Whatever entries you are seeing here, minus 3, minus 4, you take negative of those entries here and you are seeing that you are getting like all other entries are unchanged, like zeros remains like 0, 1 remains like 1, and this is your inverse. Similarly, you can check in L3 also, that is going to happen. So not only that you are able to compute inverses, but those inverses are really very easy to compute. There is no additional, what you say, computation required to compute the inverses of L1, L2. Wonderful. Now what is the third thing? The third thing is to show L1 inverse, L2 inverse, L3 inverse is lower triangular. This product is lower triangular. Okay, this is also wonderful. Okay, so what is the inverse? 1, and 2, 2, 4, 3. So 1, 2, 4, 3. Then you had 1, 1, right? This was your L1 inverse. Then a. So in the second column you had 3, 4. That was your L2 inverse. And what was there in L3 inverse? Can you tell me? What is the inverse of L3?
In 4-3 there will be 1 1.
There will be
1.
1 1.
L3 you have -1, so in L3 you will have a 1 here, correct? So this is what you have, right? And if I take the product of these matrices, L1 inverse, L2 inverse, L3 inverse, the product is 1, 1, 1, 1, 2, 4, 3, 3, 4, and 1. This is almost unrealistic, no? You just look at the first column, second column, third column of L1 inverse, L2 inverse, L3 inverse respectively. Just put those columns together in the product, and that's what you're getting as product of L1 inverse, L2 inverse, L3 inverse. So you don't even have to take the multiplication. I want you to do this multiplication once. Really, you do with your hand, pen and paper right now. You do this multiplication and convince yourself that this is what you are actually getting. This is amazing, right? You are able to construct this lower triangular matrix so easily, so beautifully. So just take a minute and just try to do this multiplication. Somebody, please, like, I want all of you to do this multiplication to appreciate this particular thing. That's okay. You finish doing multiplication. So what a wonderful thing to have here, right? So we started with these L1, L2, L3 matrices, and these L1, L2, L3 matrices were such that A times L3, L2, L1, A is equal to U. So you get A is equal to L1 inverse, L2 inverse, L3 inverse times U, right? So U is the upper triangular matrix by construction, and you wanted to prove that L is a lower triangular matrix. So in order to prove that L is a lower triangular matrix, what is it that you wanted to check? First, check that L1, L2, L3 are invertible. So they are actually invertible. You proved it. Then you computed the inverses of L1 inverse, L2 inverse, L3 inverse, and you took the product of these three inverses, L1, L2, L3 inverse, you took the product and you actually showed that the product is a lower triangular matrix. And you did this, so you constructed L. U that you obtained was anyway upper triangular. So you were able to express A as LU. So if you carefully look at this algorithm and if you carefully see what you have here as L, what you really have here as L is directly coming only from observation of A. You look at A and from observation, all the multipliers that you had when you were doing Gaussian elimination, all those multiplier information, those -2, -4, -3, those were the multipliers in the first step of Gaussian elimination. Why? Because you were doing R2 -2 R1, R3 -4 R1. So this -2, this -4, -3, these are the multipliers that you have. In the second go, what are the multipliers? You are doing these two row operations, R3 -3 R1, R4 -4 R2. By doing these two, you got multipliers -3 and -4. And the third time you got the multiplier -1, right? So you got the multiplier -1 in the third time. And these are the multipliers that you actually got. You just put the negatives of those multipliers and that gives you the lower triangular matrix. So here, in order to obtain lower triangular matrix, actually you don't have to do any calculations also. You just have to use those multipliers. Those multipliers will give rise to the lower triangular matrix. And what is the upper triangular matrix? Of course, in order to compute upper triangular matrix, you see here, you were computing, you were doing some operations on these sub blocks, right? First you did operation on 3 by 3 matrix, then you did operation on 2 by 2, and then 1 by 1, right? So you did operations, you did computations in order to find out U. So all the computations were involved in computation of U, and this U is exactly the same U that you would get after doing Gaussian elimination also. Is that right? So what we have done here is that we have shown actually is that Gaussian elimination is same as Gaussian elimination is same as LU decomposition, and you have actually able to compute L here. Is that okay? Do you understand what just happened here?
Yes.
So now the question that I really want to ask, is we just solved one 4x4 example, and in that example we saw what is really happening. In general, when you encounter this L1, L2, L3 matrices, how are you going to prove all these things about, how are you going to check these three things? Here it was easy, it was only a 4x4 case. But in general, how are you going to see that this is really going to happen for every invertible matrix set? So let us write down those formulae also. Okay, so general formulas. Let us write down general formulas. Okay, so general case of A belonging to R n cross n. Okay, so this so this is the matrix A that is given to me, and let Yk denote the kth column of matrix A. The kth column of matrix A at the beginning of step K. Okay. So that's what I have. So we want to choose Lk. So we want to choose Lk, the matrix Lk, such that what happens when I have this matrix, this column, kth column Yk. So the kth column Yk, how does it look like? I am just representing it as Y1k up to Ykk, then Yk plus 1k, so on and so forth up to Ymk, correct? These are the entries in this kth column. When I apply Lk on this, I get Lk Yk. How should this Lk Yk look? Y1k up to Ykk. These entries are not zero, and all other entries below the diagonal entry, right? In the kth column, all other entries below the diagonal entry. So the diagonal entry is Ykk. All the entries below this should become zero, right? That's what I want to do. And how will I construct this Lk matrix? The way I will construct this Lk matrix in order that these entries, so these entries are all converted to 0. So this is going to 0, so on and so forth. This is also going to 0. So I will use Ykk entry, right? So to do this, how do I construct? So Ljk. Okay, so Ljk I will construct as Ljk. I will construct as Yjk. Yjk divided by Ykk for k less than j less than or equal to m. Correct? These are the multipliers, and once I have the multipliers, how will I construct matrix Lk as? The matrix Lk will be constructed as you look at the identity matrix, and on the identity matrix apply these multipliers and row transformations, right? So I will have this matrix, so 1 up to 1 and so on and so forth. So this is the kth column. So in the kth column, what are the entries that I am going to see? In the kth column, the entries that I am going to see are L, k plus 1, k, so on and so forth, minus L, m, k. Do you understand what I have done? Is this calculation clear? So this is how I'll construct LK. And once I have this LK, then at this particular stage, I will have the kth column of A. It will get modified to this particular column. I'll make all the entries zeros. This is what is happening. This is exactly how you chose L1 in your example here, right? This is how you chose your L1 by choosing L1. So these numbers 2, 4, 3 are actually L21, L31 and L41, right? These are the numbers which are actually equal to 3, 4 and 2. So what is the matrix L1 minus L21? So minus L21 is sitting here, which is minus 2, minus 4 and minus 3, right? So this is the notation I am using. The entries in matrix cell are these entries. These are the matrix entries. So L21. So when you are multiplying by the inverse, so this is what is going to be. This is how we construct LK. I hope this is clear to all of you. So observation that we had, what is the observation? So this was the way we computed LK, and LK can be inverted. So how did you convert LK? LK can be inverted by just changing the sign, that is negating the entries below diagonal, right? So the only entries which are not equal to 0, the only entries which are not equal to 0 below the diagonal are present in the kth column. All other entries are 0. So changing the sign there does not make any change. The only change will happen in the kth column. Whatever entries are below the diagonal, you will change the sign for those entries. And after you change the sign, you will get the inverse, right? That's what was the observation. Now we really want to prove that observation. Okay, in general, can we prove this observation? Okay, so we can actually prove this observation. It is not really very difficult. So in order to prove this observation, I will introduce one more notation. Don't get overwhelmed by that notation. You will see that this is really very easy. Okay, so don't worry too much about this. So I define one more notation. I define the vector LK to be this 0 up to 0 and LK plus 1K up to LMK. Okay, so this is the vector in RM LK that I define. What is the property? The property is that first K entries are 0 of this A. Okay, so first K entries of this LK are 0 and the last n minus K entries in this vector basically are the multipliers. Okay, basically are the multipliers that you would find out in this Gaussian elimination. So whatever LK you have, you just take negative of those entries. This is how I define LK. Then you can check this. Okay, so this multiplication I want you to do now. This matrix LK is nothing but identity minus LK EK transpose. Can you check that this really happens? What is EK transpose? So EK is our standard unit vector 0, 0, 1, 0, 0. This is at the kth position. Okay, so this is our standard unit vector. So in the kth position you have. So when you take a transpose, so you have this as m by 1 vector. EK transpose will be 1 by m. So LK EK transpose will be m by m. And you have identity which is m by m. So LK becomes m by m. So LK was our m by m matrix, the multiplier. So you will get that. Can you see that this indeed happens? So what will be LK EK transpose? You tell me what is going to happen. LK EK transpose. When you multiply, what is going to happen? Tell me the first row. Tell me the first row of LK EK transpose. So this matrix is LK 0, 0 up to 0 K entries, and then you have LK plus 1 K up to LMK, right? LK, and EK transpose is 0, 0 up to 1 and 0. This is at the kth position. What is going to happen? You tell me. You tell me
Sir,
what is going.
all columns will be 0 except the kth column will be exactly same as small lk.
I'm asking, so this is m by 1, this is 1 by m, so this is m by m. Okay, so now if this is what is going to happen, I have to find out the entries in this matrix, right? So I'm going to do the matrix vector, matrix multiplication. So how will you do matrix multiplication to obtain this first entry, 1/1th entry of this product LK-EK transpose? What is it? First row here into first column here. Is that correct? So what is this entry? 0. Then first row here and second column here. That is the entry. Then kth row here and kth column here. So in the kth row you have 0. In the kth column you have 1. 0 times 1 you will get 0. This is the kth column, right? So the kth column is important for us. And all others will be 0 again because these entries are 0. It doesn't matter if you have a non-zero entry in LK. This is what. So the first row is 0. What is going to happen in the second row? You tell me.
Again.
So second row, what is going to happen? You have a 0 here and you are multiplying. So you will get the same thing, right? So 0, 0. What is going to happen in the kth row? So this is your k. Again, kth row will be all zeros, right? What is going to happen in k plus 1th row? In the k plus 1th row, what is going to happen? You are going to multiply this guy, this row with each column here. So when you multiply this, you will get a 0 here. Second time, you will get a 0 here. But now on the kth column, what are you going to get? You have LK plus 1k multiplied by 1. So you get LK plus 1 into LK and all other zeros, right? And then you will get this vector here, LMK all zeros. So this is the product that you see here. And when you subtract this from identity, you will get 1, 1, 1, all ones on the diagonal, and these guys will become negative, right? So that's what you will get. So you will get the same matrix LK that you started with. So now you will say, why am I writing all these things here? This is such a big mess of notation that I have created. But it's not a big mess of notation, because if you understand this is how I have written my LK, then it is very easy to check from here the inverse of LK. Okay, so what is the inverse of LK? So this is what you get. And the other thing that you observe now is that EK transpose into LK is 0. Okay, EK transpose into LK is 0. So now you see I have this LK EK transpose as a m by m matrix. But what is EK transpose LK? It is a 1 by 1 scalar. I am taking inner product, right? So EK transpose LK, you tell what is EK transpose LK? So EK transpose is 0, 0, 1, all zeros. So this is in the kth position. And what is LK? LK is that you have first k position 0, and then you have LK plus 1k, so on and so forth, LMK, right? So these are first k positions, and these are remaining m minus k positions. So if you multiply these two vectors in this way in the inner product, what will you get? What is the inner product?
0.
0. Okay, so this is what is happening. Now if you have this understanding, then I tell you, okay, you check this. Okay, I tell you, you check this. What is it that you want to check? You check I minus LK EK transpose. Okay, I minus LK EK transpose into I plus LK EK transpose. Okay, I minus LK EK transpose into I plus LK EK transpose. Now you check this matrix is my LK, right? This matrix was LK, and this is another matrix that I am having. What is the product? What is the product here? So you have I Then you have I multiplying here, which is plus LK EK transpose. Then you will have minus LK EK transpose minus LK EK transpose LK EK. Is that correct? That is how I'll multiply two brackets out. This guy cancels with this guy, and now I have this particular product, right? LK EK transpose LK EK. In here, I can apply matrix associativity rule. I can choose which matrices to multiply first. So I'll multiply this in between. What is EK transpose LK though? So this is actually equal to 0. You have shown it here, right? Here you see you have shown it here. This means that this is equal to identity. So you have found out a matrix here. When you multiply it on the right to this matrix LK, you get identity. So what this matrix should be? This matrix should be LK inverse, right? And what is LK inverse? Now you see LK inverse is really very easy. You had minus LK multiplying to EK transpose. You have plus LK here multiplying to EK transpose. That means that when you have a matrix LK like this, you just negate the entries here. You just negate the entries here. And by negating those entries, you are obtaining the inverse. So what you observed in the example is no just luck. This is luck for all such matrices. Right? This is an amazing thing. So if you have a matrix LK which is of this particular form, then computing inverse of that LK is no big deal. You just write it down in this form and that's it. Your job is done. Is it okay? So this notation is little cumbersome. This notation is little cumbersome for the general proof, but I think this is something that you have to understand. And once you understand this, exact similar argument where you will multiply this LK vector to EK plus 1 transpose, and you will see that this product will always be lower triangular. So what we have shown here right now in general case is that these guys are invertible. So in general case, what we have shown, these guys are invertible and you can compute inverses really very easily. I will show this to be homework. Okay, I'll leave this part as homework and you can show very easily the way I have shown it here using the similar calculations. Okay, in general case that this product is lower triangular. So that will prove that you get A is equal to LU and hence we obtain A is equal to LU. So what we can say? So we can say that given a matrix A in M by M and a vector B in Rm, and the fact, I am still using this fact, A is invertible, okay? Or I am saying that A has full column rank, okay, full column rank, okay, or the columns of A are linearly independent. So all these things are same. I'm saying that, which guarantees that there will always exist a solution. I have actually shown that there exists L and U such that A is equal to LU. And how do we know that there exists such a thing? Previous discussion. Okay, the way we have discussed, we have shown that A is equal to LU. So if you have A is equal to LU in this particular case, then AX is equal to B. If you want to solve, what we are really doing is we are solving LUX is equal to B, right? So I am writing A as LU. So this LUX, I keep it aside. I call this as vector Y. Then what do I do? First solve Ly is equal to B by back substitution. No, this will be forward substitution. So by forward substitution. And once you solve Ly is equal to B by forward substitution, use this Y, solution Y, as the right hand side of this equation. Ux is equal to Y by backward substitution. And you get the solution X of the problem that you are really interested in solving. So what is it that you want to do? We saw the construction of L. Construction of L is really very easy. And once you have the construction of L, then using that construction of L, you can construct what is U. So here, basically, the way we looked at this particular example, that example actually tells you how to construct L and how U is automatically obtained. And once you have this U, then you can solve the lower triangular as well as upper triangular system. And once you solve this lower triangular and upper triangular systems by forward backward substitution respectively, then you get your answer X, right? So this is what we will really do with the LU decomposition. And one observation here, okay, one observation here that we can see is that Gaussian elimination is actually same as LU decomposition, okay? So Gaussian elimination we can see is actually same as LU decomposition. So the two methods that you would have studied independently. So I'm very sure in LU decomposition you would have seen those difficult looking equations. You write L as L11 all zeros, L21, L22 all zeros, U as U11, U12 and so on and so forth. Then you start multiplying the matrices and then you start solving for L and U's from the entries of A and so on and so forth to obtain what is L and U. I mean, you don't need to do all these things. What you just need to observe is that this Gaussian elimination is same as LU decomposition. And in the Gaussian elimination, what are the multipliers that you use? Those multipliers entirely are giving you information about the lower triangular matrix U. And after Gaussian elimination, whatever you obtain as your upper triangular system, that upper triangular system itself is the U in this LU decomposition. So that's how you obtain LU decomposition. So Gaussian elimination and LU decomposition basically are same. And this is the construction of L and U the way I have demonstrated. And not only that, we were able to prove in the general case that these things are really very interesting, right? So the inverse of these type of upper triangular matrices is really very easy to calculate. Multiplication of all such matrices will also be very easy to show. Okay, so this actually proves that we have LU decomposition at our disposal. So any comments about this, like any doubts, any comments? You want to add something to this discussion here?
So since this is so simple, we always use LU decomposition.
Sorry, Aviraj, can you speak again?
Since this is so simple, do we generally always use LU decomposition?
Yeah, in case of square systems. So in case of square systems, you can use LU decomposition. If you know that matrix A is invertible or A has full column rank, then in case of square matrices, you can use LU decomposition. In fact, all the solvers that you have for square systems, they actually have LU decomposition in place. Okay, so many like professional solvers have this LU decomposition in place. There is a slight variation to this LU decomposition that is there. So like you use that / command in almost all the softwares that you have, right, to solve the system of equations. So if the system of equations is square, then almost always the way it is solved is by LU decomposition. And there is a small catch there. I will talk about it in whatever time is remaining. But yeah, that is what it is done typically.
Sir, for the general case, this YK we have taken the kth column of matrix A.
Yeah.
Shouldn't it be the kth column for matrix LK minus 1, LK minus 2 and A?
Yeah, it is that. So matrix A at the beginning of step K is that matrix that we mentioned.
Sir,
so this is basically LK minus 1 and so on and so forth, all this product up to L1A. Okay, so this is what I mean by matrix A at the beginning of step K. But you are right. Technically, I should write it in this pattern. Thank you. This is what I should write. You are right.
Sir, can we say conversely that if we try to construct the LU decomposition and we fail, then the matrix is actually not invertible?
Yes. You can say. So that I am not going into those details right now because I don't want to do those things right now, but you are right. So you can go through the steps that I have given you and you see where that fails. Okay, you can see where that fails. You can take two linearly dependent columns and then you see how this algorithm really fails, at what step exactly it fails. and you cannot compute the LU decomposition, you can see for yourself. It's not really very difficult. You just have to carefully come up with R, but you can do that. Is there any doubt, any issue about what we have done so far? Is this entire discussion clear to all of you? This is something which is very interesting. A lot of things that you have done in the past, I have tried to connect all those things together through this. So, like you would have learned many different names for like some of the steps. Like you would have heard something like elementary matrices, standard row operations, Gaussian elimination. Gaussian elimination can be shown like all those elementary row operations, all this. So all those things I have combined together in like one thing, and I have tried to present this. So is this okay?
Just
Yes.
one
Yes.
question
Yes.
on the linear independence. I think with respect to the previous question, so we are assuming linear independence, but
yeah,
the way to check linear independence before we start solving it, is it only the determinant route, or is there some other?
You will not go through determinant route. Determinant computation is really very difficult in real life. Nobody computes determinant. Okay, it's a highly unstable numerical operation. You don't want to do that operation. So determinant is never calculated, and determinant value, even if it is not equal to 0, that determinant value actually does not throw any light really about like how to put it. So determinant not equal to 0, that means the matrix is invertible. That is something that we all know. But that determinant being really very small number or something like that, so there are a lot of issues involved in there. Okay, so when I speak of SVD, I'll be more comfortable speaking about this determinant and relation of invertibility with the determinant and so on and so forth. So maybe I will be able to answer your question nicely after a couple of weeks. When we are done with SVD and what really happens in SVD, you will understand. Then you will appreciate that I'm not able to give the answer right now. But
okay.
Like on the face value, you take that determinant is something that we'll totally avoid. We will never do it. And at this point of time, one answer I can give is that determinant computation, like the number of multiplications and additions will be required to do to compute determinant, will involve looking at all n factorial permutations. Right? The way you expand the determinant, you are looking at all n factorial permutations on n numbers, and enlisting them, doing those multiplications, additions is computationally very expensive. So typically that is not done. Okay. So for the time being, you can assume that determinant is no role to play. As you go in advanced calculations, we will not do anything with determinant.
Okay, thank you.
But theoretically, you are right. Theoretically, you are absolutely right. Okay, that is what theoretically you have learned, and that is absolutely correct. That determinant not equal to 0 implies the columns are linearly independent. That is absolutely right. But computationally, we will not go there. We don't take that route computation. Okay, any other thing that you want to say? Anything else?
No, just a related comment. So basically then, if we have, say, a linearly dependent columns,
yeah,
then computation-wise, is it suggested to follow this entire process and then figure out that it was not linearly independent, rather than figure out first that whether it's linearly dependent or independent using the costly determinant method?
Yeah, so I will tell you this answer also is somewhat, I'll be more comfortable after I do SVD. But I will tell you something right now is that you can do this exercise on your own. Okay, you can do this exercise on your own. You can use any software of your choice. Okay, you can use any software of your choice. And what you do is you fill 4 entries of a 2x2 matrix randomly. Any random number generator that you use, whatever 4 numbers are randomly generated. That is very important. Randomly generated numbers. You put them in those 4 entries, 4 randomly generated numbers, and you check whether the matrix is invertible or not. And you record how many number of runs you require before encountering a matrix randomly generated, which is single. Do you understand what I'm saying? Kaushik?
Sir, the last part, please, once again.
So you generate a matrix randomly. So what do you mean by generating a matrix randomly? Suppose you are looking at 2x2 matrix or a 3x3 matrix or a 4x4 matrix. Okay, so a 2x2 matrix will have 4 entries. 3x3 matrix will have 9 entries. 4x4 matrix will have 16 entries. Do you understand this part?
Yeah.
So all these 16 entries in a 4x4 matrix or 9 entries in a 3x3 matrix, you generate randomly. So how do you generate these entries randomly? You use a random number generator in any software that you know how to use. You generate those entries randomly, fill those entries there, and you check whether the matrix is invertible or not. You can do that.
Yeah.
That's not a problem. And you see how many number of random matrices in this way you have to generate before encountering the first matrix which is not invertible. Do you understand this?
Yeah, got it.
Okay, you will see that almost always you will never encounter a matrix which is not invertible. The matrix that you construct will always be invertible. You see this. This is amazing. You see this. You do this experiment on your own. I urge everybody, in fact, to do this experiment on their own. And you see that if the entries are truly randomly generated, you will not encounter a matrix which is not invertible. Okay, so in numerical simulations, it translates to saying that you really have to do a large number of simulations. You have to generate large number of matrices. If you are really unlucky, then the first matrix that you generate will be not invertible. If you are really unlucky, but you will see that it will never happen. And the mathematical reason for that not being happening is something that the set of all matrices which are not invertible actually form a set of measure 0. So those people who have math background will understand this. So they lie on something which is called as determinantal variety. So the condition that you were saying, determinant is equal to 0, that give rise to something like determinantal variety. So in a very naive language, what it really means is that in R2, you are looking at some curve. Okay, in R2 you are looking at some curve. So this is really a discussion which I don't know we should be having or not, but anyway you asked this question, so I'll answer. So in R2 this is something like this is happening. Okay, so this is equivalent of n square space. In Rn square, n by n or m by m matrices, you will have Rm square, right? So in Rm square, you are looking at a set like this. Okay, so this is a set, for example. So these two curves you put together, whatever set you get, that set is looking like all the matrices which are having determinant 0. So now you close your eyes and randomly put a dart in this R2 plane. What is the probability? What are the chances that you will exactly land up on this curve? Kaushik, what is the probability?
So very minimal.
It's 0. You want to say 0, right?
Yeah.
So you close your eyes and you put a dart on this entire R2 plane, and like extremely like chances 0 that you will hit the one of the two lines, right? You can hit as close to these lines as possible, but it can go very close, but exactly going on this line. So that's why I'm saying if you are really unlucky, then you close your eyes and you hit the dart, you will be on this curve, right? Then you have encountered a matrix which is not invertible. Otherwise, you will always encounter a matrix which is not invertible. Okay, so again, these are the type of things that we will better understand when we understand SVD and how the geometry of matrices really is and so on and so forth. Right now, this is all hand waving, but that's why typically in real life applications, when you are working with matrices whose entries are corrupted by noise or whose entries are corrupted by measurement inaccuracy, so to speak, it's highly unlikely that you will be on this curve. Okay, so don't worry about encountering a matrix which is not invertible, at least in real life applications. We have to worry about that, but from the other perspective. Okay, so I'll discuss that also. But
Okay, thank you, sir.
I mean, your question is right. It is also something which is involved, and I want to answer it properly, but I can do it only after I have all those specific tools developed so that I can properly talk. So I'll speak of these things. Okay, this is something that is objective of this particular course. I'm going to speak of all these things, but it will be probably after 1 month, 2 months, when all the machinery of SVD, all the tools, all the terminology is in place, and you understand those things that I am trying to speak. But you are absolutely right. This is a very nice, interesting question. We'll answer that. And and then on the way I will also show that determinant, why I don't want to use determinant. Okay, so I'll show that also. That's not a problem. Anything else? Okay, so one thing that like Abhiraj asked is that because this looks so easy, nice to implement and all, is this what is there in the softwares? And I said, yeah, it is typically this LU decomposition algorithm that is implemented in softwares when you are trying to solve square invertible systems. But there is a catch, and the catch is the following. Okay, so if you remember the way we are coming up with these multipliers can really play havoc. Okay, so you are having this multiplier along with you, and this multiplier starts creating trouble. Okay, so I'll take a maybe very simple example, and then uh, I will. So demonstrating this is not easy. I have an example ready, but it will take time for you to understand. But what is really happening here is that these entries that are sitting here below this entry, right, the diagonal entry, so they may create problem when you are having multipliers, because the thing is that these multipliers you are obtaining by dividing, right? So the multipliers are obtained by dividing. You are looking at 1 upon these entries, right? So if you see how L was generated, somewhere I wrote the formula for L, right? So this by YKK, right? So YJK by YKK is what I'm really looking at. So for example, if you look at this particular entry, this is Y11, then I'm going to divide by Y11 in order to come up with these numbers L, right? So those number L's are going to be coming up by division of Y11. Now, if it so happens that this Y11 number is very small, okay, it is of the order of 10 power minus 4, then 1 upon Y11, so this Yjk, whatever Yj1, whatever this is. So this is of the order of 10 power 4. If this number is of 10 power minus 4, then this number is of 10 power 4. Now you see a situation where I am able to allow only 4 significant digits. I am allowed to store only 4 significant digits and the exponent. Then or only 4 significant digits is what I am really interested to store. Then this 10 power 4, if this Yj entry itself is also of the order 10 power 2, right? So then this is 10 power 2 into 10 power 4. So it becomes 10 power 6, right? So this will be 10 power 6 roughly, multiplication. And if I'm allowed to store only 4 significant digits, my computer hardware is such that only 4 significant digits can be stored, then I'm losing out on information of 2 digits. Like I'm losing out on the accuracy of order 10 power 2. And this error in calculation may lead to disastrous results when you are actually computing the solution of the system of equations. Okay, so theoretically nothing goes wrong, but computationally there are a lot of things that can go wrong. So all this computational stability, like you are dividing by a very small number, or you are subtracting two numbers which are very close to each other. So these are the operations that may lead to disastrous results computationally. Okay, so that is something that one needs to understand really carefully, and that is understood in something which is called as backward stability of computations. Okay, backward stability of computations. So this backward stability of computations is one of the most important topics in numerical analysis, in particular in linear algebra. So there is a very famous mathematician called as Alan Wilkinson. Okay, so this guy proposed that how do you measure these inaccuracies and how can you see that they are propagated forward and how do they affect the solutions. So he proposed a theory of a backward stability of computations and backward stability of algorithms in general. So it is shown that LU decomposition is not backward stable because of this. So you might have heard something which is called as partial pivoting or full pivoting. So partial pivoting or full pivoting, what do? You look at the first column, you choose the entry with the highest magnitude and you divide by that entry with the highest magnitude to avoid whatever difficulties that arise and so on and so forth. So you will try to divide by a number which is very close to zero by doing this. Okay, so this is something that an algorithm asks to do. So this is partial pivoting. So that kind of avoids the problem that you encounter here, right? So you are losing out on significant digits. So this is again very hand waving. I am not giving out any details of this, but this is something that happens. So people do. So the algorithm that is implemented in this is backward step. LU decomposition with partial pivoting. Okay. So partial pivoting only searches for the highest magnitude element in the column. Full pivoting searches for the entire matrix and gets the element and puts it in this place. So there are certain things that you have to do with this partial and full pivoting. So full pivoting turns out to be again computationally too much, and partial pivoting is kind of midway path. Okay, so the algorithm that generally is done is LU with partial pivoting. Okay, it's not only LU, but it's with partial pivoting, and it's to avoid operations of this type that you are dividing by a very small number or you are subtracting two numbers which are close to each other. These are the type of operations that are avoided. So this is very hand waving, but if any one of you is really interested in understanding all these things in details, typically I teach all these things in a course called as computational linear algebra. Okay, so this is a course. So this is a course where all these things are really taken care of, studied fully, understood fully. So this is a course which is offered in spring semester. So I offer this course in the next semester, and in that course all these things are fully understood. Like the full nice treatment is given about this backward stability and all that stuff, and how does that affect the computation of solutions. But as far as this course is concerned, I think for you think that backward stability is not really a big deal for us. Okay, because it is already taken care of by all the softwares that we use. But there is this whole branch in computational linear algebra that needs to be understood. So I know this is more confusing. It creates more confusion than solving your doubt, Aviraj. But because you mentioned it and I had 2-3 minutes to talk about something, I just talked about this. Is that okay?
Yes, sir.
Okay. So if you want to know more about it, this is my course advertisement. You would take this course, computational linear algebra, next semester, and then you get to learn all these things. Okay. So that is like a course advertisement for the next semester course. But jokes apart, this is a very important topic and we give full treatment. If you want to see everything like this done very nicely, there is a book by David Watkins, okay, which is called as Matrix Computations. Okay, Very beautifully written book, amazing book, and we use this book as a textbook for the course Computational Linear Algebra. Very nicely written, very beautifully explained all these concepts and so on and so forth. And most of the things that I talked about today, so the construction of these L matrices and everything that I was talking about today, and even the example that I was discussing, actually I have taken this material from a book which is called as Numerical Linear Algebra. Numerical Linear Algebra. These are actually the lecture notes compiled by Trefethen and Bao. Okay, so this is also one of the classic texts. Okay, so amazing textbook about these computational problems arising in numerical linear algebra. So most of the lecture today that I gave is based on the material that I took from the book Numerical Linear Algebra by Trefethen and Bao. Okay, so this is published by SIAM. This is an old book but wonderful book. And some stuff related to backward stability and all I took from David Watkins' book. So every now and again I will use these books also. Some material will be taken from these books also, apart from the two textbooks that I told you in the beginning of the course. Okay, so that is something that I will. Okay, any doubts, any further questions? Okay, so just a couple of announcements before we stop today. So I think next week, so some